everyone, it's Professor Cole, and I want to welcome you to Liberal Arts Math 1. Today we're going to look at sets, and we're going to focus on 2.1, which is set concepts. You can access these notes either in the modules in Canvas, or you can also access them through the homepage, which has the outline of the courses. So a set is just a collection of objects. We refer to them as elements. Sometimes they're also known as members. But it depends on what book you look at. Think of the United States as a set. So the United States has a collection of 50 states plus Washington, D.C., right? So the elements of the set of the United States would be the 50 states and the District of Columbia, which is Washington. This set is known as well-defined because the contents can be clearly determined. So in other words, you can name each of the states. That's what well-defined means. Or if you take any set, you can name any of the elements in that set. As opposed to an not well-defined set, which would be, best series of shows on Netflix, because the word best can be interpreted differently by different people. There's three methods that we use to indicate a set. So we can describe a set, we can write a set in roster form, or you can use what's called set builder notation. So I'm going to touch on each of these briefly. The first one, for a description, if you were given a set and you had the days Sunday all the way through Saturday, if you were asked to describe that set, we would know that that's just the days of the week. In roster form, we're going to list the elements, and we're going to use this notation, these squiggly little notations that are called braces, and we're going to place the set inside the braces, and we're going to have commas after each of the elements. So if we were to take set A as the set of the first 10 positive natural numbers, the natural numbers are going to come up quite a bit, and natural numbers are just counting numbers. Your book uses the letter N for natural numbers, and if we were to begin counting, we would start with the number 1. So if I'm looking at the first 10 positive natural numbers, my set A, capital A, we would list numbers 1 through 10 inside the braces. So I would have a brace, and then I'd have 1, 2, 3, 4, and then all the way up to 10. So when the list gets long, you can abbreviate it. You could use these 3 dots, which are called ellipses. You see them in books too, right? Or, in sentences where they want to abbreviate. And then I would put the last number in the set, which would be 10. So we understand that 5, 6, 7, 8, 9 are within that set. Set B and set C seem very similar to each other. Set B is asking for the set of natural numbers between 5 and 20. And set C is the same, except it says between 5 and 20 inclusive. So that word inclusive really makes a huge difference. Inclusive means including. So for set B, if I was to write the set of natural numbers between 5 and 20, I don't want to include 5 or 20. So I'm going to start my set at 6, and I'm going to go all the way up to 19 because I also don't want to include the 20. Set C is the same set, except it says between 5 and 20 inclusive. So in this case, it's okay to include 5 and 20 as well. So roster form is just list. Like think of a class roster. That would just be a class with the list of your names on it. One of the other ways that we can indicate a set is through set builder notation, which uses this fancy notation, this letter E, which means element. You can also say not element by putting the E with a slash through it. So it just means it doesn't belong. And the notation we use would be here in this case, this is capital A, so it's saying this set A is the set of all elements of X. And then this vertical bar here means such that the conditions X must be met in the set. So these conditions would go in here. So it might say that X has to be a natural number or a real number, and must be greater than a certain number. So for example, if we look at set E, this would be read as set E is the set of all X such that X is an element of the natural numbers and X is greater than 10. So remember, the natural numbers are your counting numbers. So I count something by starting at 1, and it says it has to be greater than 10. So we're not going to include 10. So set E would just be starting at the number 11 and then going all the way up to infinity. If we were to write set B, which is in roster form, now we're going to put this in set builder notation, we would have capital B equals X such that, so set B goes from the numbers 1 through 7. So we know that 1 through 7 are natural numbers. So X has to be a natural number, and it also has to be less than 8. If you wanted to, you could also say X is less than or equal to 7. That would be okay as well. There's some important fundamental set concepts that we need to go over. So you'll see finite sets and infinite sets. Infinite just means it goes on forever, so it doesn't stop, like infinity. So if I take off the prefix in, it leaves me with finite, which means it is ending. It's countable, it's discrete. So a finite set either contains no elements, or the number of elements in the set is a natural number, or it's countable, right? So if we look at set B, it's the numbers 2 through 12 that are even, and it's asking, is it a finite set? Why or why not? So the first thing I'm going to check is, does it contain any elements? Yes, it does. So we're going to focus on this rule right here. The number of elements in the set, is it a natural number? So if I count how many numbers are in this set, there's 6 numbers here. 6 is a natural number. It's countable. So 6 is an element of the natural numbers. So therefore, yes, it is a finite set because I can count the number of elements in that set. Some other important set concepts are sets can be equal and they could also be equivalent, but there's a huge difference. Set A is equal to set B if and only if set A and set B contain exactly the same elements. So that means that if you look at set A, it's got the numbers 2, 4, and 6. Set B also has those numbers, but in a different order. And it doesn't matter, because in order for them to be equal, they have to contain exactly the same elements. So if I was to change this 6 to a 5, those two sets would no longer be equal because they don't have the same elements. But luckily they do. So I'm going to change this back. So the number of elements in set A, they are 2, 4, and 6, and set B also has a 2, 4, and 6, so they're equal. The number of elements in each is 3, right? 2, 4, and 6 are 3 numbers. and 4, 6, and 2 are 3 numbers. And we refer to that as a cardinal number. Okay, the cardinal number is symbolized as n of a. So n of a just means the number of elements in set A. So if I look at set A below, it says it's equal to 1, 2, and 3. So there's 3 elements in set A. So n of A is 3. So the cardinality of set A is 3. And in set B, we've got the colors, red, orange, and yellow. There's 3 of them. So the cardinality, or the number of elements in set B, is also 3. Now, are this set A and set B equal? Well, they don't have the same elements, so the answer is no. But they are equivalent. So what is the difference? So since sets A and B have the same number of elements, they both have 3 elements in each, they're said to be equivalent. But they're not equal because they don't have exactly the same elements. These sets also are referred to as one-to-one correspondence. That just means, like, for every one of the elements in set A, you can match it exactly with an element in set B. So if I was to list the elements in set A, 1, 2, and 3, and then list the elements in set B, I've got red, orange, and yellow. I can now match up each of the elements in set A with a color in set B. And it doesn't even have to be those exact colors. 1 could match to yellow, 2 could match to red, and 3 could match to orange. But it's always 1-to-1. There's never any sharing of the numbers and the colors. You're not repeating anything. So this is 1-to-1 correspondence. Something important to note is that any sets that are equal must be equivalent. So if I look at that first example right here, since those two sets are equal, here set A equals set B. Automatically, that means that those two sets are also equivalent because they have the same number of elements in each set. But not all sets that are equivalent are equal. So try to think of an example, and feel free to pause the video at any time. An example that you could possibly come up with is, in that second example there, set A had the numbers 1, 2, and 3. And set B was red, orange, and yellow. So those two sets are equivalent to each other because they have the same number of elements, but they're not equal because they don't have the same elements. Another 2 important sets that you could see are the empty set, also referred to as the null set. And we use either braces with nothing inside or a 0 with a slash through it. And the opposite of that, which is the universal set, which contains all the elements for any specific discussion. And we usually symbolize that with a capital U that's cursive. That ends the lecture for 2.1. If you have any questions, please feel free to reach out to me. Also, feel free to go back and, re-listen to a part of the lecture that maybe you needed to hear again. But again, if you have any questions, reach out to me, or there's also the tutoring that's available either virtually or in person on campus. Hope you all have a great rest of your day or evening.